So this lesson has a lot of writing without a lot of math on the front page. So in order to expedite the process, we're actually going to look at the page that's already all filled in, and it should match the copy that you have. We've already talked about symmetry a lot. It's come up in previous years, but what we do in this lesson is combine what was in the original textbook 315 with 316, because it really didn't serve us to spend 2 days on it. It didn't have enough content, especially because we cover so much of the symmetry topic in previous years. So reflectional symmetry. A figure has reflection symmetry if a reflection carries it onto itself. So an example, the quilt design at the right, you can see the left side. If you were to fold it over that dashed line, it would fold directly on top of the right side. Obtain lesson 315 resource page. You all have resource pages 315. There's two of them. They're all filled in. So if you could pull that one out and see that at the same time as this, that would help. It's important to keep this page for the remainder of the course. We already put in all of the lines of reflection and things on those pages, so that you wouldn't have to do that because it was just going to be extra time. Which of the shapes on the research page have reflection symmetry, meaning that if you were to cut them down the middle, one side would reflect directly on top of the other? You'll notice several of these are regular shapes, regular hexagon, and then you get the kite, rectangle, equilateral triangle, square, isosceles right triangle, circle, rhombus, isosceles triangle, isosceles trapezoid, and regular pentagon. Now, regular means all angles and all side lengths are the same. So for your entire lives, you've looked at a square and not realized that that's a regular quadrilateral, or an equilateral triangle. That is also a regular triangle, meaning sides are the same, angles are the same. Triangles that have reflectional symmetry, they either have to be isosceles or equilateral. Types of quadrilaterals that have reflectional symmetry, the square, the rectangle, the rhombus, the kite, and the isosceles trapezoid. Now, in case you're curious on the isosceles trapezoid, if we just want to talk about that one for a second, there's lots of different trapezoids. The isosceles trapezoid is sort of the one that you've known since you first heard of a trapezoid, where this side and this side are the same length. That makes it isosceles. And if you were to draw a segment right down the middle, the left side would fold on top of the right side. The other one that's listed in there as having reflectional symmetry is the rectangle. And the rectangle has symmetry down the center vertically and across the middle horizontally. And I didn't quite split that in half, but you get the idea. What you cannot do with a rectangle, and this is probably the number one mistake that I see people make, is they try to do this. And you cannot fold a rectangle along its diagonal for a line of symmetry. And if you don't believe me, A, try to do it with a piece of paper. B, try to do it with a dinner napkin in this shape. If you try to fold it over, you end up getting this corner not folding on top of the other corner. So just a quick recap there on the rectangle especially. Problem 361, we talked about which shapes have reflection symmetry. They're unaffected when they are reflected across a line of symmetry, meaning they fold in half. Similarly, some figures can also be rotated onto themselves so that they remain unchanged. So we've got this fan shape at the right. Because it has 3 points, if you do 360 divided by 3, you can find the rotational symmetry. Every 120 degrees, it will rotate on top of itself and look identical. You could also use a piece of tracing paper or wax paper to rotate it to see that it does fit on top of itself, as long as each one of the blades are equally spaced apart and congruent shape and size. So 360 degrees will always return to the original shape, but 120 and 240 will also work. So if you were a little kid and you put a sticker on one of the blades, you would get to watch that sticker go around and it would only look the same at 360. But if it was an untouched fan blade that was perfect and all three looked exactly the same, you wouldn't know if it was a 120 rotation, a 240 rotation, or a 360 rotation. So polygons that have rotational symmetry, the regular hexagon, the rectangle, equilateral triangle, square, circle, rhombus, parallelogram, and regular pentagon. So you can look all of those up on those additional 3.1.5 resource pages. Translation symmetry. In problems 361, we talked about reflection. In 362, we talked about rotation. What if something has translation symmetry? Is there a polygon that can be translated so that its end result is exactly the same as the original object? And we would say no, because it moved. It wouldn't be on top of itself if you translated it. You can have designs with translational symmetry, but not an individual shape. Is there any kind of, I misspoke, not an individual polygon, but is there a shape that has translational symmetry? Yes, a line, because a line goes on forever. So if you drew part of a line and put the arrows on both ends, you could shift it along the line and it would continue to be translated forever because the line would go in both directions forever. All right, now here's the part we are going to actively draw. Describing symmetry. Now, describe all types of symmetry for a given polygon. For example, assume you have a regular polygon with 10 sides. So this is a regular decagon. Draw all lines of symmetry. Rotate the shape and look at it from different angles. Now, what we most often get are people that go, okay, I can do one here. And then they, oh, look, so I went from the corner to the corner. So I'm just going to go around to all the corners. And we get that a lot, that people just go around and do all of the corner splits. The thing you need to check, if your shape has an even number of sides, not only can you do corner to corner, but you can also do the center of each segment to the center of the opposite segment, and that gets missed most often. So corner to corner should work if you have odd, but if you have even, you can do the corner to corner or through the vertices, and you can also do through the center of each side. So this one, which is a decagon, has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines of symmetry. Notice I stopped because this red has already been numbered at the top as line 1. What rotations carry this polygon onto itself? So what we would do is we would say 360 degrees is a full rotation. Since there were 10 lines of symmetry, we're going to divide it by 10. And so 10 points or lines of rotation. And we would get that this shape has rotational symmetry every 36 degrees. So 36 and then 72 and so on. What translations carry this decagon onto itself? None. If I move it, it has moved. It is not the same decagon and not in the same location. All right, connections with algebra. So here we have a line, a straight line with arrows on the ends of it, just like we talked about it before. So when we want to know, does it have reflection symmetry, rotation symmetry, translation symmetry, or some combination thereof, we know it has translation. And that's because it's a straight line. So we can shift this thing up and down itself forever. So definitely a yes to translation. Reflection. Can I fold it in half? Sure. We know that in order to fold it in half, we would need a perpendicular line. So we would need something with the opposite reciprocal slope, but it's doable. So reflection is a yes. And the last one is rotation. And some people get a little hung up on this one. Anytime something can be sort of flipped upside down, it has at least 180 degree rotational symmetry. So if I brought this end all the way down to here and this end all the way up to here, it would have rotational symmetry at 180 degrees. Reflectional symmetry we can do with a perpendicular line, that opposite reciprocal slope, and translation, I can slide up and down that line. The next one has less. It has fewer options. It definitely doesn't have rotational symmetry. I can't turn this U shape any other way until I get all the way back to 360 degrees and have it look the same. And at 360 degrees, we do not consider that to be a rotational symmetry. It has to be less than 360 degrees. So that's a no to rotation. Translation, if I slide this up, that minimum is going to go up. It is not going to be on top of itself. If I slide it right, the lines will no longer be on top of themselves, heading up in both directions there. So it is a no to translational, but it's a yes to reflection. And hopefully you can see that the line of reflection would actually be the y-axis, because if I drew a line down the middle of the y-axis, I could fold this thing in half. The left side would fold directly onto the right side. Last on this row is the wave. And that wave, that curve that continuously goes on forever to the left and forever to the right, because it matches left to right, it would have rotation. I could rotate it 180 degrees. So rotation is a yes. And it would be translational, which is kind of funky because I can shift it. If you look, like right here is a maximum and right here is another maximum. So if I were to shift it that distance, then all of the maximums would line up on top of each other. If I were to shift this one, all the minimums would line up on top of each other. So it does have translational. And the last one that we want to check is reflection. And reflection is trickier because I can't just split it in half the way this one did. I actually have to make sure that I split it in half along a maximum or a minimum. So this bottom would match up on top of this bottom if I folded the left side onto the right side. You can do a lot of different lines of reflection, but it has to be through a maximum or a minimum. So reflection is also a yes. The next one, this is your inverse operation here, inverse function. Does it have translational? No. I cannot shift it and have it stay on top of itself. Even if I wanted to shift this part onto this part, it wouldn't be facing the right direction. Reflection. Is there a place where I can fold this diagram in half? And the answer is yes. The reflection line would actually be down the middle. Sometimes people will physically turn their page in order to see that the left side would then fold over onto the right side. So this is a yes to reflection. And we want to check rotation. If you can do that reflection where you can fold one side onto the other side, then it at least has rotational symmetry at 180. So this is a yes at 180 degrees. If I rotated this all the way over to here and this all the way over to here, it would be a match of the original. All right, this one is interesting. I find this one really kind of neat. It does not have reflection. And that's because if I tried to do a line here, the left side would be down at the bottom where the right side would be up at the top. If I try to go at an angle, this one would not be pointing in the same direction once it got up here. It would actually be sort of pointing that way. So this one is kind of pointing up. When I reflected it, it would be pointing sideways, so it does not reflect over a line. But I can't translate it. I can shift this maximum onto that maximum onto that maximum because it has the arrows on both ends. It will continue on forever. So it's a yes to translational. And rotation. This one is, again, kind of a funky exception to the rule. Even though I couldn't reflect it, I can rotate it. If I rotate it, this minimum becomes a maximum. This maximum becomes a minimum. So this one does have rotational, but we said not reflection. Last one, which is really just sort of a variation on the second one. This one, we can't shift it and have it stay on top of itself, so it's not translation. If I rotate it, it only looks the same at 360, so that's a no, but I can go down the y-axis and get reflectional. All right, if the y-axis is a line of symmetry of a graph, then its function is referred to as even. So if the y-axis is a line of symmetry, so if we can draw a line down the y-axis, such as these two, and we said it was a no on this one, it had to go through a maximum or a minimum, so this number 3 didn't work. We said this one didn't even have reflection. This one, the line of reflection had to be at an angle, so that's a no. And this one, our line of reflection is also at an angle. So the ones that are even are graphs 2 and 6. If the graph has rotation symmetry about the origin 0, 0, its function is called odd. Which of the graphs have an odd, what's called an odd function, rotation symmetry about the origin? So this one we said we could rotate, but it wasn't around the origin because that would move it down here below the origin, so that's a no. This one did not have rotation. This one did have rotation, and it is in fact around the origin because we would put a little dot here and this maximum would become this minimum. So graph 3 is considered an odd function. And there is one more that had rotational symmetry around the origin. This one we said no to rotation. This one we said yes. It does not happen to be the origin, which is a little tricky. But number 4 is a yes. The rotation here would work. Because here the maximums would become minimums. So you'd have to like rotate it like partway between a maximum and a minimum. So not on the origin. So graphs 3 and 4 are called odd functions. And I would put that there. All right. So hopefully this was pretty straightforward. If you do need anything more out of this section, make sure that you ask in class, and happy to go over it again. Thanks so much and see you soon.